Welcome to PicoGenius.com, where science and electronics and microcontrollers converge. Here at PicoGenius, we're going to start working with Microchip 8-bit microcontrollers for some small projects. And in particular, we're going to work with the MPLAB PicKit4 development system. The microchip we're going to work with first is going to be the PIC12LF1552. I'll give you some feature information about that. What we're going to do in this installment is we're just going to get it up and running by connecting it to the PicKit4 and doing essentially a hardware hello world program to blink an LED. Once we do that, we'll collect some analog data and we'll ship it over the I2C bus to maybe a microcontroller, or maybe ship it to a LabVIEW instrument program. But first, let's take a look at the 1552 and see what the features are. It's an 8-pin device. It has about 2K of flash memory, about 128 bytes of RAM for storing variables during your program execution. They can operate up to 32 megahertz, and they've got a nice deep 16-level stack. It's a RISC device. It has 49 instructions. It has 10 general purpose I/O pins. The reason that it has 10 pins when you only see 8 is that the I/O pins are multiplex, so they're multi-purpose. So they can be there can be more general purpose I/O pins than there are physical pins. It has 2 analog inputs which use 10-bit analog digital converters. It has a 16-bit timer counter, real-time onboard clock. It has brownout reset and programmable voltage supervisor. Both of these are used for protecting the device against low voltages. The brownout reset will actually reset the processor. If we get low voltage and you're using the PVD, it will give you an interrupt to let you know that you have a low voltage situation. You can give it a low power sleep mode and wake up from that sleep mode and save battery power. It has a clock out pin which allows you to get to an oscillator for your external circuitry if you need it, and it has in-circuit serial programming which allows you to program it without taking it out of the actual circuit. The schematic that we're going to use is shown right here. The PicKit4 has 5 connections to the integrated circuit. Of course, you have your power and ground, then you have your programming voltage, and 2 additional connections to the processor. They can be connected up at the same time that your other circuit elements are connected in the project. If you look at what that looks like in a physical configuration, here's your PicKit4, your microcontroller, and your 5 connections to your PicKit circuit. You'll notice that it's got a couple of, in addition to having the LED that it's going to blink, it's got a couple of resistors. There's a series resistor, or a resistor in series with the LED to limit the current. That's calculated so that the LED is running at about 20 mil at about 3.3 volts, which is what this processor is going to be running at. The second resistor is a 47K, and as you noticed in the schematic, it's between the 3.3 volt and the programming voltage. That's there to ensure that the programming voltage is strong during the programming phase. That can be taken out when the processor is used in a standalone configuration. So once you get your PIC set up and you get it wired to your board, you're going to need some software to do the PIC development. That software is going to be the MPLAB IDE, or Integrated Development Environment. All you have to do to use this software is go to www.microchip.com. On the toolbar, select Tools and Resources, and under Tools and Resources, select Develop. You will be introduced with these icons, and you will be able to download and install the XIDE. In addition to the XIDE, you need to download and install one other piece of software, and that's the compiler. That's called XP Compiler. It is a C compiler that you can write your programs in C, and it contains an assembler as well as the C compiler, or the XCAS assembler. Okay, so once you install that, then you'll be able to, you'll have the icon on the desktop. Your compiler and your assembler will be part of your software configuration, and then you'll be able to program your device. So let's go and look at the XIDE once it's been launched. Okay, I'm now launching the XIDE software from my desktop icon. It will take it a few seconds to load up. Okay, this is the MPLAB XIDE environment. This is the first screen that you'll see when you launch the application. So all you have to do is create a project, import an assembly language file, or write it inside of the assembler itself. So I'll show you how to do that. We're going to go New Project, and in the new project it's going to be a standalone project, so we'll select that. Now, in the standalone project, we have to pick a couple of things. The first thing that we have to pick is we have to pick the device that we're going to be using. And in our case, it's going to be the PIC12LF1552. The next thing you need is the tool that you're going to use to program the device with. In our case, I've got a PicKit4, and it is plugged into the USB port, and it is recognized by the software, so I'll select it and say Next. Now from here, you need to select a compiler, either a C compiler or assembly. In our case, we're going to be using assembly. So we're going to pick the PicKAS assembler. Next, and then we'll give it a name. We'll just call it the 1552 video. That'll be our project name. We'll say Finish. And it's going to create the project and the project files and everything you need to run this project. Okay, we have our project. We'll expand that. We have the project created, but we don't have any source files yet. So I'm going to go get a source file of a program that I previously written, and we're going to talk about that but all you have to do is right-click source files, add an existing item, and I just need to go find my item. It's in my Microchip folder. Okay, I'm going to pick the 1552 ASM assembly language program, and that's been put in the source file folder. I will expand that folder. There it is. I'm going to double click it, and it will come up in the programming screen. So there is our assembly language program in our project. Now there's a couple other things that we have to do. Since we're going to be programming this device and there's no external power supply on it, we're going to have to power the 1552 from the supply voltage of the PIC, the quick PIC device. Okay, so I'm going to go to customize here, and I'm going to pick it PicKit4 on my options categories. I'm going to select power, and I'm going to click this box to power the target from the PicKit4. I want to make sure my voltage level is 3.25 because that's the voltage level of that device. And then I say OK. And now the device will be powered by the PicKit4. First thing I want to do is make sure that my program compiles, so I'm going to use this little hammer. And I'm going to click the hammer and make sure that the program is clean and it compiles properly. Alright, the build was successful. And the program has been loaded. Alright, so it looks like it's going to work fine. When I click this green triangle, it's going to run the program. It's actually going to compile it again. It will put that program in the PIC device itself, and we will see if the LED is flashing. So here we go. Build successful, connecting to the programmer. It wants to make sure that I'm powering the device with 3.3 volts and not 5, so I'm going to say OK on that. And the program is complete. Alright, let's go and check it out and see if in fact the program is doing what it's supposed to. Before we go and look at the live demo, we need to take a look at the program in some detail so you can know exactly how it's working. This program is a simple blinking LED program for the PIC12LF1552. It uses the LED connection to pin RA0, which is also physical pin 7, as you can see in the drawing here. Let's look at what this thing does. The first line defines a target microcontroller included. It includes a specific device-specific header. That's what these lines do. Next, it defines constants. It does the configuration bits, which turns the watchdog timer off and sets other parameters inside of the processor to default values. The next thing it does is it defines it defines constants. In particular, the LED pin is defined as a 0. This means that the RA0 pin, which is pin 7, is used to control the LED. The memory locations, count 1 and count 2, are defined to store delay count information, the most significant bit and the least significant bit of our delays. The program starts at location 0, and what main does is it first sets up the I/O pins and selects the TRIS-A register bank and sets the LED pin, which is TRIS-A0, which is also RA0, which is also pin 7. Okay, so it's setting that pin as an output pin. All right, that's what it's doing. Then it sets our pointer to port A so that we can write bits out to the port A, and that's going to be port A bit 0. All right, so what it does is it calls. It starts by setting the LED on, and then it calls a delay. We're going to talk about that delay. That's this delay routine down here. And when that delay times out, it resets with the bit clear. It resets the LED, calls a delay again, and then loops and does the same thing. And it does that infinitely. The delay subroutine is a nested loop. It starts by loading a 25 into count 1 and 254 into count 2. That's what these instructions do. Then it decrements count 2, and it checks to see if it's 0. If it's not, it just keeps decrementing it. If it is 0, it falls through that loop and it asks if count 1 is 0. Count 1 is going to cause the inner loop to execute 25 times. So you're going to have 254 being decremented 25 times. So it will ask if count 1 is 0, and if not, it will go back up and it will load 254 into count 2 and count them down again. When count 1 finally becomes 0, then it returns from the delay and goes back up to the loop. So that's essentially what this program does. This program is a simple example of how to use a PIC microcontroller to control an LED, and can be modified to do all kinds of things like controller devices such as motors and relays. But primarily, it's just a program to demonstrate that you've been able to write a program in assembly, assemble it, download it to the microcontroller, and then take the development tool off, power it with a battery, and see that your microcontroller is acting in a standalone fashion. Okay, so that's the program for the Hello World. Let's go take a look at a live demonstration of the hardware. So as you can see, the 1552 has been programmed with the Hello World program, assembly language program that blinks the LED on pin 7 of the processor. What I'll do next is I'll rearrange the wiring here, and right now the PicKit4 is powering the 1552 and allowing it to operate. I will configure the 1552 standalone with a small 5-volt battery and a regulator, and I'll show you show the operation standalone. Okay, so now as you can see, the PIC microcontroller is standalone. I have it connected to a little power brick. That's a 5-volt power brick, and I'm going through a little 3.3 volt regulator to step down the voltage, and then to the microcontroller. As you can see, it's working just like it's supposed to standalone. So let me show you the schematic diagram for standalone configuration, and we will go from there. Okay, this is the schematic for the standalone configuration. You'll notice the PicKit4 has been removed, and pin 7 of the microprocessor is driving the LED through a series resistor, and the 5-volt battery voltage is being regulated down to 3.3 by the 3.3 volt regulator. This is all there is to getting microcontroller running, up and running and programmed with the PicKit4. As usual, you can get all of the source files and the schematics and stuff at picogenius.com. Be sure to like this program and subscribe, and if you're into microcontrollers, tell your friends about it, and I'll talk to you later.